Hello everyone. Thank you for joining us today. I am Amit Zadav and standing with my partner Abhishek Tiwari. We are thrilled to present the exciting outcome of our IoT internship at Emertxe Technologies. This program was a game changer for us, diving deep into the fascinating world where hardware and software seamlessly integrate to build intelligent, devices that are reshaping our daily lives. From the moment we stepped Emertxe Bridge, theoretically, our theoretical knowledge with real applications was very strong. Our capstone project, titled Home Automation Using Blink, stands as testament to our growth. In this endeavor, we designed, developed, and simulated a comprehensive IoT based smart home ecosystem, leveraging tools like PixSimLab for hardware simulation, Arduino IDE for firmware development, and the robust Blink Cloud platform for mobile integration. We created a system that not only monitors but also intelligently responds to environmental cues. Over the next 20 minutes, we'll take you on a guided tour through the foundational concepts. We explored the cutting edge tech tools. We mastered the innovative system architecture we craft, the challenges we navigated, and the remarkable results we achieved. But the end, you will see how the internship transformed us from eager learners to confident IoT engineers ready to tackle industry challenge. Let's dive in.
Good afternoon, everyone. What is meant by IoT and embedded system? This is the backbone of smart connectivity. Imagine a world where your coffee maker knows your wake up time or your car anticipates traffic jams before you even start the engine. That's the magic of smart connectivity. And it's no longer science fiction, it's our reality. In today's rapidly evolving technology landscape, from wearable health trackers that monitor your vitals 24 by 7 to massive industrial automation setups optimizing factory floors, IoT and embedded systems form the unshakable backbone driving this resolution. At its core, the Internet of Things means IoT is about empowering everyday objects with internet connectivity, allowing them to communicate, collaborate, and make decisions autonomously. Meanwhile, embedded systems infuse these devices with the computational smarts. Think of them as the brain that process data on the fly. Together, they orchestrate real-time data exchange, predictive analytics, automation, and resource optimization, all without constant human oversight. For instance, in smart cities, embedded sensors in traffic lights use IoT to adjust signals based on live vehicle counts, reducing congestion by up to 20%. During our MLTech internship, we delve into the intricate dance of microcontrollers, sensors for environmental detection, actuators for physical actions, and network interfaces for seamless data flow. This holistic understanding wasn't just academic, it directly fueled our smart home project, where we engineer remote monitoring of room conditions and intelligent controls that adapt to user preferences. Our challenge we faced early on was ensuring low latency communication to mimic real world responsiveness, something we iterated on extensively, drawing from Emertex's expert guidance. This foundation not only equip us with technical pros but also spark our passion for building systems that enhance life sustainably.
Next, move to next slide. So this is what is meant by IoT. The Internet of Things is essentially a sprawlingly interconnected web of physical devices, from humble thermostats and kitchen appliances to sophisticated industrial machines and healthcare wearables, embedded with sensor software and connectivity to collect, transmit, and act on data with minimal human inputs. It's like giving everyday objects a voice and brain, enabling them to talk to each other and to use via the cloud. These devices rely on sensors to perceive their surroundings, detecting temperature, fluctuations, motion, and humidity, and actuator too, like adjusting a well or dimming light. The data journey. The questions where the data journey of data journey starts. It zips over the internet to cloud platforms such as Blink, ThinkSpeak, or even enterprises giants like AWS IoT, where it's analyzed for insight. Users then interact via initiative apps or smartphones or dashboards on computers, turning raw data into actionable intelligence. Considering the global impact by 2025, experts predict over 75 billion IoT devices worldwide, fueling a market with trillions from energy efficient homes to precision agriculture that saves water and boosts yields. In our home automation project, we harness these IoT tents to link our simulated smart home directly to the Blink cloud. Users could glance at their phone to see live temperature graphs, light intensity levels, or water reservoir stats. Issue commands like cool the room from miles away. This setup widely illustrates IoT's power to dissolve barriers between the physical realm, your cause living room, and the digital one, your mobile notification, creating experience that are intuitive, efficient, and early prescient. We even simulated edge cases like power outage to ensure the system's reliances and adding layers of reliability that thrilled our mentors at Emertxe. Next, move to the next slide.
So defining the embedded system. So shifting gears, an embedded system is more than just a computer. It's a purpose-built marvel, a compact, specialized computing powerhouse engineered to execute a singular dedicated function within a broader electronic ecosystem, often invisibly powering the devices we take for granted. Picture the chip in your microwave that times your popcorn perfectly off the controller in a drone that stabilizes flight midair. At its heart lies hardware, a microcontroller, uh, as the CPU, volatile and non-volatile memory for data storage, and versatile input-output ports for interfacing with the world. This is married to firmware, tightly optimized software, typically coded in low-level languages like C or CPP, that's burned directly onto the chip for lightning-fast execution. What sets embedded systems apart from your laptop? They are ruthlessly efficient, low power draw for battery life, real-time responsiveness for critical tasks, and rock-solid reliability to operate solo, even offline. In safety critical apps like pacemakers or automotive brakes, a millisecond delay could be catastrophic. So embedded designs prioritize determinism over bells and whistles. In our project, the Arduino Uno was the undisputed star, the embedded nerve center of our smart home. It tirelessly pulled inputs from the LM35 temperature sensor and the ELDR, crunched numbers against predefined thresholds, and commanded outputs, firing the heater at 18 degrees Celsius or the cooler at 28 degrees Celsius, all while shipping minimum power. We even incorporated fault-tolerant logic to handle sensor noise, and nonce we refined after initial test reveal erratic readings in simulation. This hands-on fusion of hardware and software didn't just teach us theory, it instilled the discipline of creating systems that are as robust as they are responsive, priming us for the embedded world's unforgiving demands.
So, moving towards next slide, the core programming skills, that is C and C++ fundamentals. So, embarking our internship, we kicked off the C programming, the unsung hero of our embedded development. A language so close to the mental, it feels like conversing directly with the hardware. The question arises, the why C? It's lean, predictable, and compiles to machine code that files, making it ideal for resource constrained environments where every byte and cycle counts. We drill down into the essentials, signed modifiers, signed versus unsigned integers to handle negative terms or positive counts accurately. Conditional statements like if else chain for decision trees, like 20, if temperature is greater than 25 degrees Celsius, activate cooler, and loops for while constructed to poll sensors non-stop without hogging CPU. Arrays become our data vaults, buffering a rolling window of 10 temperatures reading to spot points and avoiding knee-jerk reaction to outliers. Functions modularized our chaos. Imagine a dedicated read sensor routine callable for anywhere slashing code, duplication, and bugs. Pointers were the revelation. This bad boy let us peek and poke at memory addresses, enabling dynamic arrays that resize on the fly and the pass by reference tricks to shuttle hefty structs like sensor configs. Without the memory loads of copying, we wrestled with storage classes static for persistent locals across function calls, extern for sharing globals across files, and preprocessor wizard rights like hashtag definition for tunable constants. Example, hash define temp threshold period and hash include for seamless library pools. Our memorable debugging saga, a wild pointer that changes that corporate our LCD output. We traced it back to an uninitialized address, a classic lesson in defensive coding. By weaving these three fundamentals into our firmware, we birth optimized bulletproof logic for Arduino Syn, clocking in at under 10 kBps, enough for real microcontroller and scalable for bigger beast.
So let's move to the core programming skills like CPP. We see with C as our sturdy scaffold, we ascended to C++. The evolution that infuses embedded code with elegance and scalability through object-oriented programming means OOPS. CPP isn't just a backward compatible with C, it's a paradigm shift, letting us model real-world entities as code objects, sensors as sensor, classes, devices as actuator, hierarchies, making complex systems feel intuitive. We unpack four pillars with fervor, encapsulation, bundled our sensor data and methods into self-contained classes, shielding internals like raw ADC conversions. Behind public interfaces, think private variables for calibration factors, public getters for clean access, abstraction strip line, the main loop. Instead of wiring every wire, we abstracted to temperature sensor, a dot get value parenthesis or heater activated parenthesis, hiding the gravity I2C handshakes. Inheritance means let us extend a base device class into heater device and light device. Inheriting common traits like is active while overriding specifies adding a new gadget. Just subclass and boom, plug and play. Polymorphism shown in our event handlers where virtual function let the same update state. Morph behavior based on device type, handling diverse response from unified call. Constructors bootstrap our hardware startup, pin mode setup, and initial calibrations in one fell swoop, while Destructor ensured graceful shutdowns, freeing pins and flushing buffers to prevent ghost signals. We even dab in operator overloading for sensor math like temperature or offset for initiative adjustment, a highlight. Refactoring our monolithic C code into OOP slash debug time by 40% as changes rippled predictably through the hierarchy. This OOP mastery didn't just polish our project, it aligned us with industry standards where maintainable code bases win contracts and cut cost in agile IoT terms.
So the main part arrives where we use Pixim for our simulation. In the spirit of fail fast, learn faster, we adopted Pixim Lab, peripheral interface controller simulation laboratory, as our indispensable virtual proving ground, a digital sandbox that replicates the chaos of real hardware without sparks or soldering irons. This open source gem emulates full Arduino ecosystems, breadboards, shields, sensors, and even Ethernet stacks, all ticketing in software time on your laptop. The workflow was seamless. We do author in Arduino IDE, compile to hex, and flash it straight into Pixim Labs virtual Uno. Suddenly, our code sprang to life. LEDs blinked on simulated panel. LCDs rendered crisp text and sensor feed synthetic data we could quick live, like cranking virtual temps from 20 degrees Celsius to 40 degrees Celsius to watch our autocooler kick in supported protocol out to the box. I2C bus traffic visible as a waveform. SPI clocks pulsing for Ethernet pings. One epiphany came during a late night debug. Pixim's lab of oscilloscope view exposed a UART board mismatch, flooding our serial tank data. We sync it at 9600 bps and for soon flow. By reaching physical dependency, we iterated 10x faster on honing verification rituals like unit test for each module and integration runs for the full stack. This tool wasn't just a simulator, it was our safety net, building the confidence to scale from sim to silicon, and our underscoring Emertxe emphasizes our simulation, driven development in an era of rapid prototyping.
So let's focus on the building block of an IoT device. Peripherals are the embedded system senses and muscles, the input-output symphony that turns a silent chip into a responsive orchestra. In our project, interfacing wasn't a rote wiring, it was a masterclass in protocol harmony, managing a chorus of inputs and outputs under the Arduino's beta. On the input front, the LM35 analog temperature sensor delivered precise millivolt per degree readings via ADC pins, immune to digital noise, vital for our HVAC logic. The ELDR, a photoresistor wizard, varied resistance with lux levels, triggering garden lights at dusk, means below 100 a threshold. Our serial water tank module injected realism piping UART serialized level data from 0 to 100% scale to simulate fluctuating residues complete with overflow alerts. On the output side, painted the actions means relay snap, the heater and cooler on or off for thermal bliss, solenoid walls gurgle open for irrigation, and a vibrant garden LED bloom under PWM dimming for mood lighting. So moving to the next slide, project overview.
So let's say the project overview of our home automation system. Uh, in our internship towards our crown jewel and end-to-end home automation system, a simulated smartware app that doesn't just react, it anticipates, monitors, and empower users with godlike control over their domain. This wasn't a toy. It wasn't a blueprint for tomorrow's home. Blending sensing for vigilance, actuation for ob- obedience, and cloud smarts for the eternity of our tech stack. So let's see what's eternity of our tech stack. Arduino IDE as the code for hammering C++ logic into deploying firmware. Pixim Lab as the for Pixim Lab, and next is uh, Blink IoT app, the hardware relentless loop sensing for temperature spike, dimming dusk, and tank dips links that to Blink's cloud over Ethernet and avoids edict like a flood the garden or something like that. The holistic IoT pipeline for aging device grade to cloud orchestral encapsulated our learning, scalable, securing, and evacuated of giants like Google Home, proving the virtual prototype can be prototype for the future.
So let's move to the project objectives. So first, remote monitoring. live nerve center on blink, piping temperature curves, LDR lux trends, and water level histograms updated every 5 seconds, empowering users to feel their home from afar, like a digital heartbeat monitor. Second, remote control. Frictionless dominion with app widgets toggling heater coils, cooler fans, wall gates, and light modes via virtual pins like V0 to V5, tested for less than 500 milliseconds latency to rival physical remotes. Third is smart automation. The IQ boost threshold wizards auto firing the heater below 18 degrees Celsius. Lights at twilight, LDR means less than 50 lux, or walls or low tanks less than 20% with stresses to prevent chattering. Uh, fifth, validation through simulation. Rigorous virtual gauntlet unit test for each class, integration smoke runs, and load simulation mimic 24 by 7. Ooh. Flagging 95% of bug prep hardware, slashing iteration cycles. We hit every mark, not just ticking boxes, but exceeding with extras like historical data logs. These objectives weren't checkboxes, they were our compass, validation of prototype that functional today, evolvable tomorrow, and a launchpad for careers in IoT innovations. Let's move to the system architecture and technology stuff.
Think we should start. We can cover this in our demo. So let's start directly demo. Abhishek, can you stop sharing your screen?
Yes, 1 minute.
Am I visible?
Yes.
So first of all, let's connect our virtual computer. Here we will select component comp 4. Okay, I think it's not working. Let's select component comp 2 and we'll create a bridge for it. We'll using this for the serial tank. So now let's dive towards Pixim. We'll load here. First we'll configure. Wait a minute. Mm, Let me try again. I think there's a bit issue with Pixim. Okay, let's try to load our hex file directly. Load Pixim. changing spare parts. Let it be. I have recorded one video previously when it was working. So now we don't have any option. I will show you the video for a demo. Here is the temperature system, Ethernet and LCD, I to C. Here is LED and LDR sensor too. LDR sensor senses the intensity of light and according to it adjusts the uh, brightness of our LED. And here the LED is presenting the is the cooler is on or off. It is currently on, and it also showcasing the cereal tank. Now the outlet of our cereal tank is on, and here it is showing the volume of our water, and also displaying whether the uh, tank is on or off. The outlet flow is on, and the cooler is on too. And here we can see the temperature, that is 27.37 degree. And now the outlet of cereal tank is off, and we can see the brightness of LED using LDR sensor. And that's the demo of our project. And here here is our code, that is final.ino. So our ION file, which you see on the left, acts as a high-level manager. When it needs to open the inlet valve, it simply calls the function enable underscore inlet. It doesn't know how to talk to tank. It just knows the function exists. How the low level details is hidden on the encapsulated inside the serial tank.cpp file, which you see on the right. This is the only file that knows the specific serial commands for the inlet valves is 0x00 and enable is 0x01. This abstraction is powerful. If you got a new tank model with different commands, we would only read this serial tank.cpp. The main file, that is .ino, would not change at all. So we have made this separate parts of code. So we should not able to change everything in the code. So that's it. But sorry for inconvenient. Don't know the Pixim won't work. But when it was working, we have recorded the video. This is the only demo which we can see you, show you. Uh,
So thank you. Thank you from the depths of our hearts for your generous times and rapt attention today. Your presence made this sharing all the more meaningful, and we hope our tale of IoT intrigue and embedded exploits has sparked your own curiosities or ideas. A profound bow to Emertxe Technology, their world-class curriculum, bleeding edge labs, and unwavering mentorship were the wind beneath our wings, turning novices into navigators of the connected cosmos. This internship didn't just teach skills; it instilled a lifelong hunger for innovation, the kind that says, "What's next?" So, thank you.